So at this point, we've talked about linear motion, so displacement, velocity, acceleration. And we've talked about rotational motion, angular displacement, angular velocity, angular acceleration. And all we want to do now is put those two things together. So how can we relate when an object is moving? How can we relate its linear motion to its rotational motion? And so let's say that we have an object sitting here at point P. And point P sits on this disk, and this disk is rotating about an axis at its center, and it happens to be rotating counterclockwise. So our curve here is showing us the direction of rotation for this disk. And so if we think about our object as it moves here at point P, as it rotates, as our disk rotates through some angle, then our object at point P will move across some distance, and how long that distance is going to be directly related to how far of an angle our turntable turns through. So if we label r as the distance from the axis of rotation, so here's our axis of rotation, here's how far we are away, so this distance here is r, then what's called s is our arc length, so literally just a length of some section of the arc of a circle. And that distance s, the arc length, is going to be given by r times your angular displacement. So the farther away you are from the center, the larger the arc length you've got to go around if you cut out the same angular displacement. So if you think about sort of going all the way around the circle, basically if you went all the way around the circle, then you would cut out an angle of 2 pi. And of course, you would then go around an arc length that's equal to the circumference of the circle. And sure enough, 2 pi times r is the circumference. So this equation makes some sense in terms of thinking about how this linear distance that your object is going to move, it cuts out some particular angle. Well, how about speeds? So if I'm now thinking about, again, my disk as it rotates counterclockwise, well, I know from my right-hand rule, if I curve the fingers of my right hand in that direction of rotation, then my thumb's going to point out, which tells me that my angular velocity points outward. And I want to think about the speed at which, so the linear speed of my object as it goes around this circle at point B, how that relates to the angular speed at which the disk is rotating. And again, r is still going to be the same distance from the axis of rotation, and I see that the linear speed v is going to be equal to r, that distance, times the angular speed. Now you'll notice one of the things that, let's just go ahead and emphasize now, we know that our linear speed has units of meters per second, r has units of meters, omega has units of radians per second. So this sort of tells us that, again, radians has this property that says it's there when I need it to be there, and effectively it goes away when I don't need it to be there. So that this is, so that dimensionally the units on both sides of this equation are the same. Well, now if I want to think about the linear acceleration, the first thing I might want to relate that to is the angular acceleration. That makes sense given our previous slide. Well, if I look at this angular acceleration, this linear acceleration, my first instincts might be, well, it's a vector, so let me break it up into x and y components. But what we're going to do is we're going to choose to use a slightly different coordinate system to break this up into. And notice we're going to pick a coordinate system where one of our positive directions lies in the direction of the velocity, and the other one is perpendicular to the velocity. And so now if I want to break my acceleration up in this coordinate system, what I notice is I've got a component that lies along the line parallel to the velocity vector, and a component that lies perpendicular to the line of the velocity vector. And so what I can do then is think about these two components. And let's talk about this one first. So AT happens to be what's known as the tangential acceleration. It's the component of the acceleration parallel to the velocity. So my tangential acceleration, in this case, my velocity is pointing in the direction sort of up and to the left here. My tangential acceleration is either going to point along this line up and to the left or back in the other direction down and to the right. But the tangential acceleration is going to lie along the same line as the velocity vector. The magnitude of that tangential acceleration component is going to be given by r times alpha. So again, r is our distance away from the axis of rotation, and alpha is the angular acceleration. So the function of the tangential acceleration is it indicates whether an object is speeding up or slowing down. So one of the things we talked about when we first started talking about acceleration is we said that acceleration tells us about the change in velocity, and there are three ways that we can change the velocity vector. We can make its magnitude greater because the object speeds up. We can make its magnitude less because the object slows down, or we can change the direction of the magnitude because the object's turning. The tangential acceleration, because it lies along the line of the velocity, is telling us about whether the object is speeding up or slowing down. So in this case, so for this particular example here, notice that the tangential acceleration points in the same direction as the velocity. That means my object is going to be speeding up. Well, the way it speeds up is by spinning faster. And for it to spin faster, that means that the angular acceleration has to point in the same direction as the angular velocity. So by thinking about, in our example here, the fact that the tangential acceleration lies in the direction of the velocity, that tells me that the object has to be spinning faster, which means I can figure out what the direction of the angular acceleration is relative to the angular velocity. If, on the other hand, the tangential acceleration pointed back this way, so pointed opposite the direction of the velocity vector, then that would obviously tell me that my object is slowing down. Right? So our same rules apply here. All we're doing is slightly changing that speeding up means that the velocity and the tangential acceleration component point in the same direction. Slowing down means the velocity and the tangential component of the acceleration point in opposite directions. So if my object was slowing down, then the tangential acceleration component pointed back opposite direction of the velocity. So that tells me how, or that gives me this first component, AT. Well, what about this second component? Well, for starters, AR is the radial acceleration. And again, I notice that it's the component of the acceleration that's perpendicular to the velocity vector. So one of the things I know is that if it's perpendicular to the velocity vector, it can't be telling me about the object speeding up or slowing down, and in fact, it's indicating whether the object is changing direction. Now, one way that I can calculate the magnitude of radial acceleration is by r omega squared. So simply by the fact that it's rotating. So I have some non-zero angular speed, then I have to have a radial acceleration. But if I plug in, and if you think from a couple slides back where we said that v is equal to r times omega, and all I'm going to do is solve that for omega, that gives me v over r, square that. So I get this expression, and I substitute that in. I get one of the r's down here cancels the r up there, and I'm left with v squared over r, and I recognize that this is what we refer to as centripetal acceleration. So centripetal acceleration is just the special name that we were giving before to the radial acceleration when we were working our centripetal motion problems. So in both cases, whether we call it the centripetal acceleration or the radial acceleration, the same rules apply. One is that that acceleration component points towards the center of the circle, or towards the axis in which we're rotating around. And then I can also calculate its magnitude by either r omega squared or v squared over r. So if you know the angular speed, you can use r omega squared. If you know the linear speed, you can use v squared over r. And in either case, it tells me how my object is changing its direction as it turns around some point. Now, if I know two perpendicular components of a vector, I can find the magnitude of that vector by Pythagorizing. So in this case, I can get the magnitude of the linear acceleration by taking the tangential acceleration squared plus the radial acceleration squared. So again, given that I know what these expressions are now in terms of my angular variables, I can calculate what the tangential and radial acceleration component are using my angular variables and then Pythagoras to figure out what's going on or what the magnitude is of my linear acceleration. I can also figure out the relative direction of my linear acceleration to the direction of the velocity by using the inverse tangent. So again, if I know those two components, I can use the inverse tangent to tell me about a direction. And so what we can do is we can figure out, well, what's the angle between the linear velocity and the linear acceleration as our object moves around with both linear and rotational